Alright, so let's look at a classic example of an optimization problem. What is an optimization problem? An optimization problem is any type of problem where you're trying to maximize a quantity or minimize a quantity. You might want to maximize your profits. You might want to minimize the amount of materials going into a design. Alright, so we're looking at optimization problems. And let's take an example of a problem over here. And in this problem, it says Chuck is building a rectangular sandbox next to his fence. He has 12 feet of plastic edging that can be cut to any length. If the fence forms one side of the sandbox, what is the maximum area that can be enclosed? What are the dimensions that maximize the area? Let's identify some keywords. We're building a rectangular sandbox. We know we have 12 feet of material to use, and we want to maximize the area. So let's try a couple of quick examples. Here's my fence. And what do I know? I know I have 12 feet of material. So, let's see here. What if I make this side 2, that side 2? Then the length of this side would have to be, well, you had 12 feet total. So far we've used up 2 sections, both of 2 feet. So that's 12 minus 4, which is 8. So this side is 8 feet. What would the area of that rectangle be? Well, area is length times width. Our length is 8 feet. Our width is 2 feet for a total of 16 feet squared. Alright, so there's one example. I know I can build at least a sandbox of 16 square feet. Let's try a second possible dimensions. Instead, let's say here's my fence again. And instead, let's say I make this side 4 feet. Then that also makes that side 4. And then this side here, well, I had 12 feet of material. I've already used 2 sections each of 4. That's 2 times 4 is 8. 12 minus 8 is 4. So this side here is also 4 feet. What would our area here be? Our area still would be length times width, 4 feet, times the width, 4 feet, which is a total of 16 feet squared. So does that mean all the rectangles, doesn't matter what size I build them, they're all going to be 16 square feet? My first 2 did. Let's try one more example. So now, let's say I wanted to build a skinnier one. Let's say I make this one 1 foot, which makes that side 1 foot. So far I've used up 2 feet of my material, so this must be 10 feet. What would the area here be? Length times width, 10 feet, times 1 foot, which is 10 square feet, which is not the same as 16. So it looks like we know we can build one of 16 square feet, and we know we can build one smaller. The question is, if we're going to maximize, could we build one that is bigger than 16 square feet? Well, to do this, let's look at some modeling. Alright, so let me link to my model here. And in my model, I want you to notice here's our fence, here's our rectangle, our sandbox, and notice the areas do look like they are changing. I could have a really wide, skinny rectangle. I could have a really short, wide rectangle, and it looks like the areas definitely are changing. Well, how can I find this maximum area? Well, let's put some analytical geometry on this problem. First thing I want to do is look at our constraint here. I want you to notice I've built this to have a blue wall. There's our blue wall there, and we have 2 greens. And let's look at our constraint. When I tied it to the geometry, I was able to make this x-coordinate 17, that x-coordinate there -5, and the difference between those x coordinates is 12. So this total line segment here has a length of 12, and for our example, we'll assume it's 12 feet. Down here, I want you to notice as I change this side, notice the green sides do get bigger, and the blue side then gets shorter, and vice versa. And I want to point out that the wall, if I look at the dimensions, change in the y coordinates gives the length of that side on both of them. The change in the x coordinates gives the length of that side there. And I want you to notice that they will always add up to 12. Sorry about that. Let me move that up there where it's visible. So notice, doesn't matter when I move these will always add up to 12. Okay, now what we're really interested in is the area of the rectangle. So what I'm going to do here is I'm going to plot the length of this side here versus the area of the rectangle. So let me plot that. I'm going to show you the point right here. So over here, I have x is the length of this side here, and a is the area of the rectangles formed. I'll show you here, I'm using the actual coordinates. There's the length of that side there. It's the same as that right there. And then I am actually multiplying the two areas, the lengths together. The length and the width is right there. And then I am plotting these 2 points. So watch what happens to this point up here as I change this around. Notice right now, move this back to 4, or close to 4. Close to 4 right here. Looks like our area is, 16. And just notice as I move it down, this one just not skinny, tall rectangle, doesn't have much area. It gets more and more area as I go up. Then what happens? It looks like I'm hitting the peak of my area about right there. And then as I start making it wider, my area actually starts decreasing again until we get a very wide, short little rectangle. So let's look at what is called the locus of all those points. If I was to look at all those points that blue dot over there on the right is chasing, it would show up as the locus. Okay, and we can see the area increases, the length of the blue side gets bigger, but then it hits a peak there, and then actually starts decreasing again. Okay, so let's do the college algebra. And let me get a whiteboard out here. So let us do the college algebra. Okay, so I'm back. Let's look at the college algebra of this problem. And here I've already drawn our model again. And let's see here. We went ahead and made this length of that side there x. For right now, let's call this side here y. Well, we also know the length of that side there is y. So how many x's do we have? 1. And how many y's do we have? 2. And we end up with x plus 2y. That must equal 12. We only had 12 feet of material. This is referred to as the constraint. Let me respell that. It's the limitation. We only have so much materials to use. And then our area of that rectangle would be, the length would be x, the width would be y. What's the problem with this? It has 2 variables there, 2 independent variables. So what do we need to do? We need to get rid of one of those variables. So let's take our constraint equation, x plus 2y equals 12, and let's solve it for y. First thing I'll do is subtract x off both sides. Excuse me. So I get 2y is equal to minus x plus 12. I move the x over the other side. I'm going to divide each term by 2. So I get y is equal to, I'm going to write that as a fraction, minus 1/2 x plus 6. Okay, so let me clear up some chalkboard here. We had our area of our rectangle being x times y, and then we also had y being minus 1/2 x plus 6. So now, if we look at rewriting our area function now is going to be, let me just clean this up a little bit more here. Our area function is going to be x times y, which is minus 1/2 x plus 6. Let's distribute through. I get minus 1/2 x squared plus 6x when I distribute through. Let's see how this function matches up with our model, our locus. So let me plot our college algebra function. And I want you to notice here is our function. The blue dotted one is there, and if we were to hide that real quick, let me hide it. You see that it matched up perfectly with our locus. So the next part of this lecture will be how to find that maximum area using college algebra. But for now, I just wanted to show you that it existed and that the areas actually do change depending on your dimensions.